I'm here to talk about Finagle. Maybe you've heard of it. It's a project from Twitter, but we'll get into that in a second. First, a little bit about me. This is my dog. I'm the CTO of Buoyant. We're working on a bunch of open source infrastructure. Most of it's kind of stuff we learned at Twitter, so we're a team of mostly ex-Twitter engineers. I was there between 2010 and 2015 when I led the observability team to the monitoring team. We open source Zipkin and a bunch of projects out of there. And then moved on to traffic, which is related to what I'm going to talk about today. Been involved with Finagle for a while. We just open source a project called Linkerd, we'll just discuss a little bit today. And we've been playing with Kubernetes for about a year now. Really like it, so we'll talk a bit about that as well. So, brief overview. Without further ado, let's talk about microservices a bit. And certainly at Twitter, as well as most other companies we've talked to, are only considering microservices because they're focused on scale. But just as frequently, they're focused on scaling their teams. They want to have many developers working together without crushing on one code base, one deploy chain, which is great, right? So we have this new paradigm for writing software. Unfortunately, we have a bunch of problems there. These are the things we don't get for free by moving microservices. Anyone who tells you that you're going to get performance for free by moving to microservice is wrong. So we have to compensate for these things. All right. So back to this quote. Basically, we have these big computers called data centers. Google runs huge computers called mega data centers across the world. And now we have to build tools to compensate for this fragility, this complexity that we lose. So if we could just build one massive computer and run it and make sure it didn't go down, that'd be a much better world, but that's not the world we live in. In microservices, this specifically means that things are going to break. Software you didn't write, software you didn't compile or configure or deploy, hardware you can't even touch, networks that you have no idea how to configure, any of these things will break in the middle of the night in surprising ways. They may not just go down, they may get very slow. And your customers still need to use the site. And so that's really the goal that, of operating a system, is that you shouldn't have to wake up because something breaks in the middle of the night. In microservice specifically, this means we need a resilient communication. This has to be done at a communication layer. So we have tools that make resources. If we lose a host, things can balance. But in microservices especially, we have a communication problem. Which brings us to an old model here, the OSI model. Hopefully you've seen it before. But it gives us this nice way to think about communication problems and the tools that arise there. So starting at the top, we have layer 7. Hopefully this is the code you write. These are the things that matter here are the languages you choose, the testing frameworks you choose, the libraries you use. This makes it easier to do your business. And at the bottom, we have all of the hardware stuff. So we have data centers that we hopefully don't have to operate ourselves. We have networking that has to be configured. And we have an orchestration layer that is, at the end of the day, responsible for getting a process running somewhere. And in the middle of that, we have this kind of communication concern. What we at Twitter called RPC. It's kind of a bad word in some circles, but I promise you it's not. Just talking about requests and responses. And we have this session layer that really we don't have tools around at wide scale. We're used to things like TCP dump and kind of low-level debugging tools for operating on hosts. But once I'm dealing with tens of thousands of hosts, these tools just don't scale. And so we need a new set of tools here. At the session layer, we're dealing specifically in requests. So if I'm talking to 1,000 endpoints, or 100 endpoints, or even 10 endpoints, I need to do connection pooling, load balancing, and retries, timeouts. All of these problems are on the request level and not on the connection level. So we need a way to map from requests to connections. Again, from layer 5 to layer 4. And so Finagle kind of deals in this layer. So I'm going to talk about this for a second. It's a library for the JVM, written in Scala. It's built on Nitty, which is a kind of tried and true JVM networking library. It's asynchronous. And it's been around since about 2010. How many people were using Twitter in 2010? Okay, a few. Was it up very frequently? Right? So a big part of that story for Twitter was moving onto Mesos and Aurora to solve the scheduling layer, much in the same place that Kubernetes does. And similarly, we had Finagle come up, which was first launched in production early 2011, and is now how every service at Twitter is built. And it's not just Twitter. A lot of other companies have picked this up. So this really does operate at scale every day. A lot, millions and millions and millions of requests go through this thing. At the heart of it, Finagle gives us a programming model. It makes it easy to write services. So here is a little bit of code. Creating a client, talking to the user service, and then I'm serving an HTTP service on port 8080, and it's just proxying requests to the user service with a timeout. So that's nice, elegant. If you like functional programming and types systems, and Scala is great. What you don't see in the slide, however, is any of this. And this is all taken care of by Finagle. So we don't see service discovery integration there. We don't see circuit breaking, back pressure timeouts, TLS. Any of these things are not in your application code anymore. And so Finagle has this kind of mature system for dealing with these things. I'm going to talk about some of the motivations that got us into this situation. So this is another ex-Twitter engineer, Jeff Hodges, wrote this great post on distributed systems. And one of the things I really like here is he says, it's slow is the hardest problem. It's down is easy to debug. I know where to go find the thing that's down. But when the manager comes to you and says, the service is slow, where do you start? In a big distributed system, this is very hard. If I have n machines talking to n machines, I have m by. So here, I have 5 servers talking to 4, or 5 clients talking to 4 servers. I have 20 connections that can become slow, brittle. So what happens if one of these servers becomes slow? So we have this one thing that's hardware is kind of buggy or the network's congested, and things become slow to here. What you too frequently see is that this causes pressure on the rest of the system. So we have widespread outages based on single points of failure, even in a distributed system. So one problem that we can solve here is we can load balance. And in the in the kind of layer 4 world, we load balance over connections. In this world, we're load balancing requests, and we have more information around request latency, and we can make better decisions. And so if we start with kind of a simplistic round-robin load balancer, a single slow host that falls out of our timeout, so if we have a second timeout, if we have a single instance fall out of that timeout, we drop to 95% success rate. And so we need new load balancing techniques, specifically exponentially weighted moving average, UMA, gets us over 3 nines, just by changing where we do load balancing. So doing it at the request layer again, and not at the connection layer. Also, we can do things like retries, lots. We have more tools at our disposal when we operate at the request level. And so once we now know that something's slow and we have to go, our success rate's dropped a little bit, where do we go debug this? We need a tracing system. And so it's very easy in a monolithic application to go put a print line in every function and see where something is slow. You put time information. In a distributed system, I may not be able to deploy the thing that I need to go put a print line in. And so we need a principled way to instrument our stack to emit traces. So here we see a call graph. Maybe these things don't need to be serial. Maybe those can be parallelized. And so having tools where we can visualize and see how much time in a particular call, where those resources are being spent, becomes very valuable to debugging problems at scale. However, once I have a tracing system instrumented, I also have topology information. So we had this problem at Twitter where we'd put all of our dependencies into a spreadsheet. And so we'd go to every team and say, OK, please list all the services you talk to. And then we'd go in an incident, and it would be wrong. Not wrong because people made mistakes or lied, but because these things change dynamically all the time. And so we need tools to just tell us, OK, well, tell me who's talking to whom. And so a tracing system like Zipkin, for instance, gives us the tools to be able to not only do debugging, but do kind of org-wide tracing and topology information. One of the other features Finagle gives us is layer 5 routing. So I can route requests. And so if you saw in our code before, we referenced the user service, S-users. What I didn't say is it's in Kubernetes in the prod namespace on the HTTP port with this service name. Or I didn't say it's in Zookeeper in this path or etcd in this path. And so we don't want to have our applications know about that level of detail, about where we're looking things up. And so we need a principled way to write our code that's not environment specific, and then have a mechanism for actually binding these things into place. And so we do this through a system called delegations or delegation tables, simply dtabs. And so this becomes a rewrite syntax for saying, well, whenever you see the S prefix, let me go look this up in Kubernetes in this way. And in fact, if I'm going to go look at this docs, why don't I just override that here? And so DNS is kind of at this concrete level of naming. We use the Kubernetes API as a concrete level of naming. Other people use Zookeeper, et cetera. But this shouldn't be part of your application logic at all. And when we do this, it unlocks surprising potential. We now have the ability to do per request routing. So I can make an HTTP request and say, instead of using the user service, use v2 of the service. We just saw Kelsey's demo where he did canary deploys. Well, what if we weren't actually exposing those to end users? What if I wanted to just test my code just for my requests? Somewhere deep in the stack, so this may be 3 or 4 levels deep in the stack. As long as this header context propagates with requests, we now have a way to do dynamic routing. Same thing for debug proxies. Again, I can't go put a print line in a service I don't own necessarily. And so what if I want to say, well, when you're going to call the slorb service, send it to the debug proxy, which will then go forward back to the service that should be talking to. This allows us to do things like timeout injection, failure injection, debugging, filtering of results, which becomes very powerful when you're in a large organization. So do you have to write your app in Scala to use all this? Hopefully no. So introducing Linkerd. We've open sourced this about a month ago. It's on GitHub. Come check it out. And what we've done is package a bunch of the logic in Finagle, a lot of the power in Finagle, into a separate process that's configuration based. So you don't have to write code to use, and you don't have to know any Scala to use it. And you can get a lot of this functionality basically for free. So instead of connecting directly to a service, you connect to localhost, or you connect to Linkerd in a predictable way, and it will manage service discovery for you, timeout management, TLS, a lot of this stuff. And it's totally pluggable, so we can be kind of platform agnostic and plug into various systems. And we get all of these things for free, right? In Kubernetes specifically, we've been running this as a sidecar. I think I'd like to see this move elsewhere in the stack, maybe as a daemon set sort of integration point. But it actually fits quite nicely as a sidecar, and we've been able to crank this down so it's not a big performance hit there. And so now, instead of having services talk directly to each other, they just talk to localhost, and we manage communication there. So if we have our service, we have an incoming route, which just forwards everything to the local service, and everything outgoing, we go look it up in the Kubernetes API before dispatching the requests. So here's kind of all it really takes to get going. In Kubernetes, we allocate a service, and we don't give it an IP. And that allows us to do our own load balancing natively. And then here we have basically the configuration I just said. We're going to talk to the Kubernetes API over SSL. We have some very static route. All HTTP requests go to this local port. And because it's a pod, we know we use localhost. And then on the outgoing side, we have some rewrite rules again to say, well, take all the HTTP things and route them into Kubernetes. Again, I said this project's been open for about a month, so it's still pretty new. There's a lot of things we'd like to do, especially around Kubernetes integration. I'm really excited about the third-party stuff coming into 1.2. That's going to allow us to store a lot of the configuration state in the API. We're really excited about gRPC. I think that's going to be a really powerful tool for service builders, but Linkerd allows you to be in a hybrid world where not everything is in gRPC, but you can still get a lot of the same value. And we have cluster-wide routing controls. A bunch of the things that are in Finagle natively aren't really exposed from the config yet. And so we're going to be working on exposing that over the next few months. All right. Does that all kind of make sense? Any questions yet? OK. Well, we're going to do a little bit of a demo. It's pre-recorded because I'm super jet lagged and didn't trust myself to do it live. So we'll see how that goes. What we're going to do is we're going to launch an application into Kubernetes. We're going to use Linkerd to control it. And so there's a web front end, it's all written in Ruby, and two backend services, a book service and an author service. A colleague of mine, Kevin, has a huge bookshelf and wanted a way to manage it, so that's our demo app. What we're going to do is we're going to launch a new version of the book service, Books v2, and we are going to canary that and test it, do everything we should. And then we have this other namespace called Helium, which gives us kind of the tracing side of this and a nice UI, which is really just demoware at this point. But we'll be open sourcing some of that in the near future too. All right, and here we go. All right, so we're going to look and see that we have nothing in the in Kubernetes yet. We have two namespaces, and we're going to launch the app. And so we're launching replica controllers and services for everything. We only have two external services so that we can access the UI. And then everything else is internal headless services. We see that here as well. All right, so we have a bunch of authors instances and books instances, and we have our little control plane. Now we're waiting for the IP to come up. Once we get our external GKE IP, we can go see the admin page. So this is the control plane. And we're logging here. We have no events yet because we've sent no traffic through the system. Now we're going to find our admin page, I believe. So this is actually connecting to the Linkerd running on the web server. And we should be able to see, again, nothing going through the system yet. We haven't even allocated clients. So there's no hard-coded configuration there. All we have is the server interfaces. Now we're going to go to the book service. So this is our lovely books app, a bunch of books and a bunch of authors. And what we see, we've connected to it. So now we see requests going through Linkerd. And we see that we have clients allocated for books and authors. We go to the tracing view, and now we have a topology. So we have the front end as well as our backend servers. And this is reflecting the traffic that's actually been sent through either of these routes. So we have a few requests each. It's a very nice D3. All right. Now we're going to launch our V2 instance. We're going to allocate a service for it. But we're not going to connect that into the front-end load balancer. So this just exists on its own, and no traffic should be going to it. We see that we have V2. And what V2 does is it adds on Kubernetes to all of the book names. The growth hackers say this will make us a lot of money, so we're going to go test it out. And we send requests to the site again, no changes, right? We haven't actually linked this into anything at this point. Now we're going to add a request header into the browser so that only my user can see this. And we're going to reload, and boom, we're talking to the new book service. And we also see now that we have requests going to the new book service. We're going to turn this off, back to the old world. So that's a good canary case, right? I've now tested new code without actually showing it to any external users, deep in the call graph. Now we're generating a bunch of load just to throw load at the site. We're going to go change routing centrally. And so what we're going to do is we're going to say, when I actually talk to the book service, split it between both of these services. I want to send most of it to the old book service and just a little bit to the new book service. So we have a 9-to-1 ratio that we're going to send here. As soon as we've done that, I think we can go to the admin page. Oh, and we'll start to see that here the weights are going to change. Once we click through, now we have two instances here. We have the old cluster and the new cluster. No, most of it's going to the old cluster, and a little bit is going to the new cluster. And here we see the same thing, right? Now I'm looking at the request graph. Most of it's going to the new one, or the old one. Some of it's the new one. Now we're going to split it evenly. So we can do weight-based controlling. We don't have to just do this via tags. And now we'll see it converge kind of quickly. And so now we have about the same load going to each the new and the old. And if we were to go to the site, which I don't know if we do, but if we refresh it, we'll see about a 50% chance of having new code. And so now what we're going to do is something, next. We're going to show that this is going to even out dynamically. We'll see this kind of rebalance to show that load's being split. Okay, and now what we're going to do is we're going to refer the new book service, v2. And if that doesn't exist for some reason, we're going to fall back to the old one. And so we can use these alternate rules to say, OK, v2 or fall back to v1. As soon as we change this, we're going to see all the traffic go to the new service. Boom, right? And we're going to go here. We refresh. We're going to be on the new one. We go here. We're going to see traffic slowly moving on to the new one, the new port. This is because it's aggregated over all the events we have. So it's slowly showing that weight shifting. And now we're going to go tear the rug out under it. And I think we should do that without seeing any hit to success rate. This should all just work without failing requests or any sort of fragility there. Which also means we don't actually have any health checks set up here. We're not doing the polling slow start thing. This can start up, be slow, and Finagle will actually deal with that natively. So if requests can't be sent, we don't fail them. We just route them as we can. All right, delete the service, and immediately we have traffic failing over the new, back to the old service. And so this gives us a flexible mechanism for canarying on a per request basis, doing global routing via staging and things like that. And this is basically a blue-green deploy, or canary, depending on how you think about this. And so these are things that can only really be done at the request level, at layer 5. And so I hope to see a new set of tools built around this, around RPC specifically. And so frameworks like gRPC are a great push in that direction, but we still have all these old HTTP applications that need to work in this model. And with that, I invite you to come check out the site. Linkerd.io has a bunch of docs on this, specifically around the delegation stuff, which is particularly interesting. You can come hang out with us on Slack. Feel free to email me or follow me on Twitter, and Linkerd has a Twitter account as well. I'm not that good at Twitter, so you don't have to. But with that, I'm happy to take questions if there are any. Yes?
Is all the routing done on the client side, or is there some other process?
So that's actually part of the sidecar, right? So as those headers propagate with requests, right? If we pass them through on all the service calls, the router itself is going to say, OK, I need to send this to the user service. Let me rewrite that service there. So it's on the client side of, before I send the request, but not in the application or in the browser or anything like that. There's another hand? No? All right. Well, thank you for your time.
Thank you all for